Voyager 1 really did turn around in deep space. It happened billions of miles from Earth, only minutes before NASA shut down its cameras forever. But the spacecraft did not reverse course, and nothing was chasing it home. That turn produced the pale blue dot. The unexplained discovery came more than 2 decades later when a surviving instrument detected a faint, persistent signal in interstellar space. Scientists can use the signal to map that space. What they still do not know is exactly what creates it. Cape Canaveral, September 5th, 1977. A Titan Centaur rocket lifted Voyager 1 away from Earth, carrying technology that now looks almost impossibly primitive. Its computers had only a tiny fraction of the memory inside a modern phone. Commands were stored in systems designed before personal computers became normal household objects. The spacecraft carried no repair crew, no spare probe, and no realistic expectation that anyone would still be operating it nearly half a century later. Its original assignment was much smaller than the story it eventually became. Voyager 1 would fly past Jupiter, continue to Saturn, study both worlds and their moons, then complete its primary mission. The launch window was special because the outer planets had arranged themselves in a rare geometry. A spacecraft could use each planet's gravity to change its speed and direction, turning one launch into a tour of worlds that would otherwise require far more fuel. The spacecraft itself was a strange combination of delicacy and durability. A dish antenna, almost 4 meters wide, handled communication. 3 radioisotope generators supplied electricity from the heat of decaying plutonium. A long instrument boom kept magnetic sensors away from electrical interference generated by the spacecraft. 2 thin antennas stretched out to detect plasma waves. Bolted to its side was a gold-plated copper record containing sounds, music, greetings, and images from Earth. The record was designed for a finder who might never exist, in a future so distant that no human language could be assumed. Yet the machine carrying that message still had to survive a much more immediate test. It had to cross the radiation around Jupiter, navigate the rings and moons of Saturn, and keep its antenna aimed at a planet that would soon become just another point near the Sun. Voyager 2 launched first, but Voyager 1 followed a faster route and overtook its twin before either reached Jupiter. The names reflected which spacecraft would arrive first, not which one left Earth first. In March of 1979, Voyager 1 swept past Jupiter. Its cameras showed turbulent cloud bands, the thin ring around the planet, and moons that looked nothing like the dead rocks many people expected. Images from the mission helped reveal active volcanoes on Io, the first active volcanism ever observed beyond Earth. Europa appeared crossed by strange lines and unusually free of large craters, early clues that its icy surface was young and possibly hiding an ocean. The volcano discovery came from a detail near the edge of an image. Navigation engineer Linda Morabito was examining a picture of Io when she noticed a bright plume rising above the moon's limb. What looked at first like another moon was material erupting hundreds of kilometers above the surface. Jupiter's gravity, working together with the pulls of neighboring moons, was flexing Io and heating its interior. That one observation overturned the assumption that a small world far from the Sun should be geologically quiet. It also established a pattern Voyager would repeat throughout its life. The mission would reach a place described by reasonable models, return a measurement that did not fit the simple picture, and force scientists to add complexity. Those discoveries would have been enough to define an entire mission. Voyager still had Saturn ahead. The crucial decision at Saturn involved Titan. Scientists wanted a close look at the giant moon because it possessed a dense atmosphere, something unique among moons known at the time. Mission planners therefore chose a path that would send Voyager 1 close to Titan and then above Saturn. Titan refused to give the cameras a clean view of its surface. A thick orange haze hid the landscape below, but Voyager measured a cold, nitrogen-rich atmosphere containing methane and complex organic chemistry. The results made the moon more interesting, not less. Decades later, the Cassini spacecraft and Huygens lander would return to reveal rivers, lakes, and rain made from hydrocarbons. That route delivered valuable measurements of Titan's orange atmosphere, but gravity demanded a price. Saturn bent Voyager 1 sharply north, lifting it out of the broad plane where the planets orbit. There would be no Uranus or Neptune encounter for this spacecraft. Its planetary tour ended there. The apparent ending created a different mission. Voyager 1 was now following an escape trajectory toward the dark space above the solar system's planetary disk. It had become an interstellar probe almost by accident, even though reaching the actual interstellar boundary would take another 3 decades. By 1990, the planets behind Voyager had collapsed into points of light. The spacecraft was roughly 3.7 billion miles from Earth, beyond Neptune's orbit and moving farther away every second. Its cameras were no longer scientifically essential. Keeping them warm and operational consumed electricity that could support instruments needed for the long journey ahead. Before those cameras were switched off, Carl Sagan and other members of the Voyager imaging team pushed for one last photograph. They wanted the spacecraft to look home. Pointing the cameras toward the inner solar system was not a casual decision. From Voyager's position, the camera would be looking dangerously close to the sun. Bright sunlight could damage the imaging system. The sequence required careful planning, and the resulting photographs would contain almost no planetary detail. Earth would be smaller than a single picture element. That lack of detail was the point. On February 14, 1990, Voyager One rotated its science platform and aimed the cameras back across the solar system. It photographed Neptune, Uranus, Saturn, the Sun, Jupiter, Earth, and Venus. Mars was too dim to appear, Mercury sat too close to the Sun, and Pluto was both small and poorly positioned. The complete mosaic became the first family portrait of the solar system seen from the outside. Inside one image, Earth appeared as a tiny blue point caught in a scattered ray of sunlight. Every city, argument, ocean, border, and human life occupied that almost invisible speck. The photograph is famous now, but receiving it was slow. Voyager did not send a modern image file through a broadband connection. It stored data on board, transmitted it across billions of miles at a low rate, and relied on NASA's deep space network to recover the pieces. The full family portrait required several communication passes and did not finish arriving until May. The image of Earth was also partly an optical accident. The pale ray surrounding the planet came from sunlight scattering inside the camera. A flaw became part of the photograph's meaning, placing the planet inside what looked like a beam across the darkness. 34 minutes after taking the Earth images, Voyager 1 powered down its cameras forever. This is the real turn in the title. The spacecraft rotated to take a final look. It did not fire its engines and begin flying back. Once the photographs were complete, its main antenna remained aimed toward Earth while its trajectory continued outward. The distinction matters because Voyager has always needed to point in two directions at once. Its instruments face the environment around it, while the large dish antenna must remain aligned with a planet that grows fainter and more distant every year. Small thruster pulses keep that radio beam on target. If the antenna drifts too far, the most distant human-made object could continue functioning while Earth loses the ability to hear it. The cameras were gone, but Voyager 1 was not blind. Its remaining instruments could sense charged particles, cosmic rays, plasma waves, and magnetic fields. Those measurements would become far more important than another photograph, because the spacecraft was approaching a boundary nobody had ever crossed. The sun does more than illuminate the planets. It continuously releases the solar wind, a thin flow of charged particles moving outward in every direction. Those particles carry the sun's magnetic field and inflate a huge bubble called the heliosphere. Earth, Mars, Jupiter, Saturn, and even distant Pluto move inside that bubble. Far beyond them, the solar wind finally encounters plasma and magnetic fields originating between the stars. The boundary where the solar wind gives way is called the heliopause. Pictures often draw it as a smooth shell. Nature had other ideas. Voyager. One crossed the termination shock in 2004, entering the heliosheath where the solar wind slows, compresses, and becomes turbulent. Scientists expected the final journey across the heliopause to produce several unmistakable changes. Particles from the sun should fall away. Galactic cosmic rays from outside should increase. The direction of the magnetic field should rotate as the spacecraft moved from a solar environment into an interstellar one. During 2012, two of those predictions arrived dramatically. In late July, particle levels changed, then returned to their earlier values. It looked as if Voyager had touched the boundary and pulled back, even though the spacecraft itself had never changed direction. The boundary was moving. That detail is easy to underestimate. The heliopause is not fixed at one permanent distance like a wall built around the sun. Solar activity changes the pressure inside the heliosphere. Conditions in interstellar space press from outside. The boundary can expand, contract, ripple, and sweep across a spacecraft that continues steadily forward. So Voyager could appear to enter a new particle environment and then leave it without making a U-turn. The frontier moved over Voyager, not the other way around. On August 25th, the change became permanent. Lower energy particles associated with the heliosphere collapsed. Some fell by more than a factor of 1,000 compared with measurements from 2004. Galactic cosmic rays rose to the highest levels Voyager had recorded. Everything pointed toward interstellar space except the magnetic field. Its strength increased sharply, but its direction changed by less than 2 degrees. The clean rotation predicted by many models simply was not there. For months, the team faced an uncomfortable question. Had Voyager crossed the heliopause, or had it entered another strange region still inside the sun's bubble? This is where the story takes a turn that the instruments themselves could not settle. Voyager 1's main plasma spectrometer, the device that could have measured the surrounding plasma most directly, had stopped working just after Saturn in 1980. The spacecraft had reached the most important plasma boundary in its history without its dedicated plasma instrument. Another instrument offered a way around the problem. The plasma wave subsystem uses two long antennas extending behind the spacecraft. It does not scoop up plasma and measure its speed like the failed spectrometer. Instead, it detects electrical oscillations produced when electrons and plasma move together. The frequency reveals density. A higher pitch corresponds to more electrons packed into the surrounding plasma, much like the note from a vibrating object changes when its physical conditions change. For years, the instrument had detected little that could provide a direct density measurement at Voyager's location. Then, the Sun supplied the missing experiment. A major solar eruption had thrown a disturbance outward through the heliosphere. More than a year later, that pressure wave reached the region around Voyager One and made the local plasma oscillate. In April of 2013, the plasma wave instrument detected the ringing. The pitch showed that the surrounding material was far denser than the plasma inside the heliosheath. Researchers searched backward through older recordings and found a fainter event from late 2012. When they reconstructed the timing, the evidence converged on August 25th. As the date, Voyager One entered interstellar space. The crossing had happened. The magnetic field simply had not behaved the way the cleaner models predicted. Scientists now think the field immediately outside the heliopause can remain distorted by the nearby solar boundary. Imagine magnetic field lines as elastic bands wrapping around a moving bubble. Crossing the skin of the bubble does not guarantee that those bands instantly snap into the undisturbed direction of the wider galaxy. The solar system can leave a wake and a magnetic imprint beyond the line we call its edge. That interpretation produced a testable prediction. If Voyager continued far enough, the measured field should gradually rotate toward the direction expected for less disturbed interstellar space. Researchers could compare that trend with observations from other missions studying the heliosphere from far closer to Earth. The result is a useful reminder of what a model is supposed to do. A model is not a sacred picture that nature must obey. It is a compressed description built from the evidence available. Before Voyager, every direct spacecraft measurement had been made inside the heliosphere. The first probe outside the boundary supplied the missing perspective, and the model had to change. That explanation resolves part of the original confusion, but it also changes the picture. The heliopause is not a perfectly clean wall separating two environments that never mix. Voyager entered interstellar plasma while continuing to detect signs that the Sun was influencing the region around it. Even the phrase, "left the solar system needs care." Voyager 1 is outside the heliosphere, so it is operating in interstellar space. It has not traveled beyond the distant Oort cloud, the enormous population of icy bodies still gravitationally connected to the Sun. NASA estimates that reaching the inner edge of that cloud may take roughly 300 years, and passing through it could take tens of thousands more. Voyager had crossed the Sun's plasma frontier, not every possible border of the solar system. The pressure waves from solar eruptions kept producing occasional whistles in the data. They were scientifically valuable because each one measured the density around Voyager, but they appeared only at irregular intervals, leaving enormous gaps in the map. Then researcher Stella Koch-Ocker and her colleagues filtered years of plasma wave observations and noticed something much weaker. Beginning around 2017, a narrow line persisted in the data. It was faint, almost a single tone, and it continued between the louder events caused by solar pressure waves. As Voyager moved through interstellar space, the tone shifted slightly. Those changes tracked variations in electron density across distances no spacecraft had ever sampled before. The original study followed that emission over about 10 astronomical units, with measurements spaced on average by only a small fraction of 1 astronomical unit. Instead of waiting perhaps a year for a strong solar disturbance to make the plasma ring, researchers could follow the density every few days along Voyager's path. That turned a sparse set of isolated readings into a connected profile. Peaks and dips in the tone exposed density changes that would otherwise have been invisible. The line was weak, but its persistence made it scientifically valuable. What comes next is the part that still does not have one accepted answer. Researchers can use the signal, but its precise physical source remains unsettled. The emission might come from plasma oscillations, excited by the natural thermal motion of particles. It might be a form of quasi-thermal noise detected by the spacecraft's antennas. Later research has examined how those mechanisms could produce the narrow line and what features would distinguish one explanation from another. Both possibilities involve ordinary plasma physics, but ordinary does not mean simple. The antennas, the spacecraft, the local electron distribution, the surrounding magnetic field, and weak natural fluctuations can interact. Voyager was never designed around the assumption that this exact signal would become one of its final scientific products. Researchers are effectively learning how to use an aging instrument in an environment nobody could test on Earth at full scale. Only one spacecraft is collecting this particular data along this particular route. Voyager. 2 crossed the heliopause in a different direction and carries a working plasma spectrometer, which provides an important comparison, but 2 tracks through a vast 3-dimensional boundary are still only 2 tracks. Separating a universal property of interstellar plasma from a local feature near the heliosphere is therefore difficult. That is very different from saying scientists have no ideas. They have plausible mechanisms, equations, and comparisons with plasma measurements closer to Earth. What they lack is a final model that explains why the emission remains so persistent and why it appears with the exact properties Voyager records in this unfamiliar environment. The word sound can also mislead. Interstellar space is not carrying an audible hum to a microphone. Voyager detects electrical waves in plasma. Because their frequencies fall within the range human ears can hear, researchers can translate the data through a speaker. The result sounds like a rising or steady tone, but the spacecraft is measuring electron motion, not recording noise through air. And there is no evidence the signal is artificial. No coded message has appeared. Nothing in the published data suggests another spacecraft, an alien beacon, or an object following Voyager. The genuine discovery is less cinematic and more useful. A probe built in the 1970s found a new way to map matter between the stars. If you enjoy documentaries that investigate the real science behind impossible-sounding space headlines, subscribe. The verified version of this story is stranger than the viral one, and Voyager still has more to tell us. The narrowband emission changed the mission from occasional snapshots into something closer to a continuous survey. Across roughly 10 astronomical units of travel in the original study, the signal traced density fluctuations on scales that revealed structure and turbulence in the very local interstellar medium. 1 astronomical unit is the average distance between Earth and the Sun. Voyager measured this faint line across a path many times longer than that, sampling as it moved through a region no replacement mission can currently reach. That matters because the heliosphere is shaped by pressure from both sides. The solar wind pushes outward. Interstellar plasma, neutral atoms, cosmic rays, and magnetic fields press back. To understand the size and shape of the bubble around our Sun, scientists need to know the density and magnetic conditions beyond it. The bubble matters to Earth because it changes the particle environment throughout the solar system. The heliosphere deflects or reduces part of the galactic cosmic ray population, while allowing other particles through. It is better described as a changing filter than an impenetrable shield. Voyager's measurements help researchers understand how that filter interacts with the material surrounding the Sun as our entire solar system moves through the galaxy. They also provide a nearby example of a problem that applies to other stars. Many stars produce winds and carve bubbles into the interstellar medium. We observe some of those structures from far away, but Voyager lets scientists sample one from inside and just beyond its boundary. The local details can improve the way astronomers interpret distant stellar environments that no spacecraft will visit for generations. Voyager's measurements suggest the space immediately outside the heliopause is still changing with distance. Electron density rose after the crossing, then remained within a similar range while fluctuating. Those variations can help researchers study turbulence, pressure fronts, and the way disturbances from the Sun continue traveling after they have left the heliosphere. The irony is hard to miss. Voyager turned around in 1990 to show us how small Earth looks from far away. Then it continued outward and discovered that the boundary surrounding that tiny world was more complicated than expected. Neither moment required the spacecraft to come home. Its value came from leaving. Keeping it alive has become an experiment nearly as remarkable as the science. Voyager One was designed with redundant systems because engineers knew a repair mission would be impossible. They did not expect those backups to be tested across almost 5 decades. In November of 2023, Voyager stopped returning readable science and engineering data. The radio carrier remained, which meant the spacecraft was still transmitting and responding to commands. But the information inside the signal looked like gibberish. Engineers traced the problem to the flight data subsystem, one of the spacecraft's onboard computers. About 3% of its memory had become corrupted. A single failed chip held part of the software needed to package data for transmission. The cause could not be confirmed. The chip may have been damaged by an energetic particle, or it may simply have worn out after 46 years. Either way, nobody could replace it. The only tools available were commands transmitted from Earth. Each instruction took more than 22 hours to arrive, and the response required the same journey back. One troubleshooting cycle consumed almost 2 days before engineers could learn whether a change had worked. There was another complication. The missing code would not fit into any single unused section of memory. The team divided it into pieces, placed those pieces in different locations, and rewrote references throughout the software, so the fragments could still function as one system. It was the digital equivalent of rebuilding a damaged part of a machine, while the machine remained in motion, using a manual written in an obsolete language with nearly 2 days between touching a control and seeing the result. In April of 2024, readable engineering information returned. By June, Voyager One was again sending science data from all 4 instruments that were operating at the time. The recovery did not solve the mission's oldest problem. It only returned the spacecraft to a race it cannot win forever. Voyager 1 receives electricity from radioisotope thermoelectric generators. Heat from the decay of plutonium is converted into electrical power. The system has no battery charger waiting at the next planet, and its output falls by about 4 watts every year. Engineers have saved power by shutting down heaters, instruments, and other components in a carefully planned order. Those choices are never as simple as unplugging an appliance. A heater drawing electricity may also prevent a fuel line from freezing. A small motor that seems expendable may be the only practical way to reactivate an instrument later. Even the thrusters are aging. Residue has accumulated inside narrow fuel tubes, forcing controllers to use longer pulses and switch among different sets. In 2025, engineers revived roll thrusters that had been considered unusable since 2004. The repair required restoring their heaters and managing the risk that a cold thruster could fire before it was ready. The test succeeded. Hardware dismissed as dead for more than 20 years became a working backup again. Then, during a planned roll maneuver in February of 2026, Voyager 1 experienced an unexpected power dip. NASA warned that another drop could trigger automatic fault protection, shutting down components and forcing a risky recovery. On April 17th, engineers sent commands to turn off the low-energy charged particle experiment. It had operated almost continuously since launch, measuring ions, electrons, cosmic rays, pressure fronts, and changing particle conditions beyond the heliosphere. The shutdown left Voyager 1 with 2 operating science instruments. One measures magnetic fields, the other is the plasma wave subsystem, the instrument detecting the persistent interstellar emission at the center of this story. NASA kept a small half-watt motor associated with the particle experiment running, preserving the possibility that the instrument could someday be reactivated if engineers recover enough power. The agency also described a larger energy-saving plan nicknamed the Big Bang, designed to exchange several powered devices for lower power alternatives in one coordinated operation. The April update scheduled tests on Voyager 2 first, followed by a possible attempt on Voyager 1 no sooner than July. Until NASA confirms the outcome, anything more dramatic is speculation. That is the pattern running through the entire mission. The truth is repeatedly squeezed between 2 temptations. One is to declare that Voyager has found nothing strange because every measurement must eventually have a physical explanation. The other is to treat every unexpected signal as proof of something impossible. Science lives in the uncomfortable space between them. The persistent emission is real. Its use as a density tracer is supported by the data. Candidate explanations exist, but its detailed origin remains open to investigation. That uncertainty is not a failure. It is what happens when the first instrument to enter a new environment reports conditions no earlier instrument was present to measure. Voyager 1 never turned around to investigate a pursuing object. It rotated its cameras for one final portrait, powered them off, and kept moving away. Years later, its surviving instruments reached a plasma frontier that behaved differently from the neat boundary scientists had drawn. The pale blue dot and the interstellar hum are separated by decades, billions of miles, and completely different instruments. Yet they belong together in one important way. The photograph showed that everything humans had ever known occupied a fraction of a pixel. The plasma signal showed that even the invisible boundary around that fraction of a pixel was still largely unexplored. Voyager 1 is now more than 15 billion miles from Earth. A command needs about 23 hours to reach it. The returning signal is so weak that giant antennas in NASA's deep space network must pull it from the background noise. The transmission carries very little data by modern standards. That limitation shapes the science. Engineers schedule which instrument speaks, decide what information deserves the narrow connection, and use enormous radio dishes to recover a signal transmitted with less power than many household light bulbs. Every useful measurement arrives only because the spacecraft maintains its pointing and Earth happens to be listening at the right time. Eventually, the power will fall too low. The plasma tone will vanish from the data, the magnetic measurements will stop, and the spacecraft will continue silently toward the stars. But it will not turn back. It will carry the golden record, the final photograph stored on Earth, and the evidence it transmitted from a region no human instrument had entered before. The mystery is not why Voyager 1 changed direction. It is how a machine that never did manage to change our view of the space surrounding home.